Howdy, people. We're going to spend some time on oscillations and waves, and specifically we're going to talk about things that waves do, and in two main areas, what are called reflection and superposition slash interference. So here's what I mean. Here goes a wave pulse. Look, this wave pulse we'll say is propagating to the right. There's its direction of motion. All right, when it gets to the end of this stuff, and this stuff is the medium, whatever this stuff is, when this wave gets to the end, for sure, part of the wave reflects. And reflects means bounces back in the direction it came from, which I'm not going to write, but maybe you will. All right, that's what reflection means, bounces back in the way it came from. So scenario one is that the boundary, and so we'll call this the boundary. When this wave gets to the boundary between one medium and another medium, what's over here in this other medium? I don't know. But scenario one is the boundary. Is boundary spelled like that? Maybe. Is what's called a fixed end. I'll represent that like this. And scenario two is the boundary is a free end. And I'll represent that like this, open circle. And what that really means, I mean, it can quite literally mean like that well, I'll show you in this simulation. I mean, we can have, look, a fixed end where I'm going to send, how about this? I'm going to send a pulse. I'm going to make that a nice tall, but let's do this. We'll do normal. Yeah, great. Let's see what this pulse looks like. Perfect. Pause! All right, so look, this end is quite literally held in place, all right, and not allowed to oscillate. Okay, well, what happens is when this wave pulse gets there, yeah, here it comes. Wait, so this particle here, you know, pulls up on this one, but this one isn't allowed to move up. So when this one pulls up on this one, the green one pulls down on the red one. That's the nature of interaction. When red pulls green up, green pulls red down. But green can't accelerate up. So what that means is it means that red has to accelerate down. And so this wave pulse gets yanked down below equilibrium when it reflects back. Okay, here's another fixed end over here. That's not allowed to oscillate. So this wave pulse keeps reflecting and turning from a crest or a peak into a trough. Crest into a trough. Okay, that happens at fixed ends. So at fixed ends, when after this crest bounces off this boundary, it comes back like this as a trough and goes back that way. And assuming there's no, I mean, we're saying there's no energy loss here, because note that the amplitude of this crest and trough are the same size, right? Same amplitude. So we're not losing any energy. We're just, so all of this wave is reflected back in the direction it came from. All right, now the other thing we can have is a loose end instead of a fixed end. And so watch what happens here. Now we get the green one at the end is pulled up by the red one at the end, but the green one is allowed to oscillate. So the upward pull from the red one pulls the green one up, and the green one accelerates up, right? And what happens is that thing yanks up there, and then, well, everything gets pulled back down, and that crest stays a crest. Now look, here's a fixed end, so that crest turns into a trough. Let me slow this down a little bit. Here's free end, trough stays trough. Here's fixed end, trough turns to crest. Here's free end, crest stays crest. Okay, so when we get one of these loose ends or free ends, what we get is whatever the wave was on the way in, it comes back the same way. Now, some kinds of waves, aren't waves on strings. And it's not that there's, a physical object that's allowed to oscillate or not. Sometimes it kind of is that way. So, when sound bounces off a wall, there's that last particle of air, right? Here's a wall. Here are particles of air in a row, right? These particles oscillate back and forth like that because sound's a longitudinal wave. And so this last particle, well, can't move that way. So that means the wall acts like a fixed end. All right, and so the nature of the reflection of, quite literally like the echo, the reflection of sound off the wall will turn a peak into a trough. Okay, so that's reflection that happens in a couple of ways. Now, here's a different phenomena, and here come two wave pulses coming toward each other. This one this way and this one that way. And we'll call this one, we'll say this one has an amplitude A, and this one has an amplitude B. All right. When they are superimposed, which means at the same place at the same time, these things interfere. And when they interfere, what happens is you end up getting a amplitude that's bigger. And it's actually bigger just simply by the sum of those two amplitudes. And they interfere what we call constructively. And that means that there's a peak with a peak, or a trough with trough. If amplitude gets bigger, then that's what we call constructive interference. Okay, so anytime two of sort of the same wave feature interfere, what we get is constructive interference. And look, we could have these two waves. Look, I can take two different waves, clone, and, well, I could have these waves interfere constructively if they look like that, right? If we have peaks lining up with peaks, or if we have troughs lining up with troughs. All right, so as long as these waves match up feature for feature, then we get what's called constructive interference. As opposed to, here comes a peak approaching a trough. This one with A, this one with B. All right, what you get here is that these two things would interfere and give a result something like that, where this amplitude is A minus B. And these things, when they are superimposed, they interfere what we call destructively. Just like these two waves would interfere destructively. Clone. If we had them lined up, sure. These would interfere completely destructively. I can't put them on top of each other because we got that opaque background. But if these two waves were at the same place at the same time, and peaks lined up with troughs, and the amplitude of each one of those things is the same, the result of that interference would be nothing. Nothing at all. These things would add up, these waves would add up to nothing. Okay, so we can show that sort of thing on our wave simulation here. Right, watch this. I'll take another pulse. All right, look, here comes a peak toward a trough, and they're going to interfere. I'm going to step through here. Watch what happens. We keep stepping through, and there's going to be some time. Yeah, boom. That's when one peak is right here and the other trough is right there. We get an interference result of nothing. But super importantly, that means that energy doesn't disappear, right? We still have to conserve energy. So look, these things keep on going. Okay, now we're going to get, let's see, now we're going to get peak and peak, and they're going to interfere, and at some instant there, boom, we get the addition of those two amplitudes. And here's what's important to note, right? I want you to make sure we note this. Look, here comes a trough to the right. Trough was here. Trough keeps going. All right, so these waves don't bounce off of each other. These waves, hard to tell here which one was which coming in. But, oh, unless I do this, unless we do something like this, watch this, manual. I'm going to make a big old, hang on, restart. A big old tabletop peak there, okay? And then I'm going to make, hang on, a big old, get down there, fine. And then a little dinky thing like this. Now watch this. Here comes that peak towards that other peak. Yeah, look, we can see that exact shape of that first one added. So that first one is like, right here kind of, right? And we add this amplitude to the amplitude of that thing above it, and we get that interference pattern, right? And notice our little spike keeps on going. Now we're going to get that big trough. And look, there's our little peak riding across it and keeps going. Let's speed this up a touch. Now we're going to get two troughs. And there's our little trough riding on the big trough and keeps going. So real important to note that these waves keep on traveling, even though they can be temporarily at the same place at the same time. They keep propagating through this medium. They don't bother each other. They don't affect they affect each other while they're interfering, but those waves keep on propagating. Good thing to note. Okay. So here's a case where, let's say, we want to show. How about? Oh gosh. How about we want to show? Why is this happening? So we're going to show that we have a peak that looks, what's happening here? Like this. And how about a peak that looks like that? I don't know what's going on here. Let's try this. And okay, did this work? And so this thing's coming this way and that one's coming this way. When they interfere, we're going to get something that looks like that, at least for an instant. And then the things keep on going. Big block that way, a little nub this way. Okay. Here's another one. So this we'll do as a destructive case. So we'll do this thing like that, and we'll do this thing. We'll change it to a little triangle. This thing is coming like that, this way. And so for an instant, we'll get that little interference result. And then the two things keep going on their merry way. Okay, so interference is, simple to model. It has some pretty profound effects, some pretty profound phenomena that you can observe with interference. But as a practical thing, we just have to know that waves can interfere either constructively, where we get displacements or amplitudes on the same side of equilibrium that add up to a bigger amplitude, or destructive interference, where we get trough peak or peak trough interference, where for an instant we get a result that has a smaller amplitude than the ones it started with. But also important to note that these waves keep on propagating in their original direction of motion. There's this idea of phase. In phase, what we have to be able to interpret there are a couple of things. One of them is we might talk about different locations on a wave. Like, for example, let's talk about this location and this location and, well, how about this location and this location? And maybe even this location. So these different places on a wave, well, have what we can call a phase difference. All right, and what that refers to is this idea. One idea is that a full oscillation is representative of 2 pi radians, like going around a circle once. Okay, so what we might talk about sometimes is, well, what's the phase difference between different locations? And what that means is how far along a wave is one location relative to another. So for example, if we were to say like from A to C, well, those are half of a wave away from each other. We would say that's a pi radian phase difference. Or we might say it's a 180-degree phase difference because 2 pi radians is like around a circle once, and that's 360 degrees, right? We could say that A and D have a 2 pi radian phase difference or a 360-degree phase difference. We might say that B and E also have a 2 pi radian or a 360-degree phase difference. We might say that, well, like, let's see, B and C, that's a quarter of a wave, so it's a quarter of 2 pi. That's pi over 2, okay? Now, we also might talk about the phase difference or phase shift of actual different waves. All right, so if we say here's wave 1, here's wave 2, here's wave 3, wait, you can notice that these waves, it's like there is a way to match them up. Can I undo these? Can I ungroup them? Yeah, look, this one, right? We could match this one up like that, but then if it was shifted over to where it was, I think it was shifted over to here. Notice we've shifted it over half of a wavelength, right? So from 1 to 2, waves 1 and 2 have a pi radian phase difference. And note that wave 3, it looks like wave 3, it looks like, let's see, wave 3 was shifted over this much because this trough is this trough. Looks like it was shifted over. So 1 to 3, they have a quarter of a wave, a pi over 2 radian phase difference. So we can talk about the difference in phase in any two actual full waves or different waves, right? What we have to be able to recognize with this phase stuff is that when will waves interfere constructively versus destructively? All right. Well, waves will interfere constructively when their peaks line up with peaks. So that means if they have a phase difference of, say, nothing. But it also could be if they're shifted by an entire wavelength, right? So look, we have this guy like this. If I shift it over an entire wavelength, then those two things are back to interfering constructively. So we could also put, these could be 2 pi radians out of phase or 4 pi radians out of phase or dot, dot, dot. But they'll interfere destructively when they're half of a wave out of phase. So that's pi radians out of phase or let's see, or 3 pi radians out of phase. Look, let's see if we can do that. Here's in phase, right? Here's 1 wave out of phase, right? Sorry, 1/2 wave, that's pi radians. Here's 2 pi radians, but here's 3 pi radians back to peak interfering with trough. And what I'm doing is I'm comparing what's happening here and here. All right, those are out of phase at 3 pi radians out of phase. These are, but we would say these are back in phase because trough lines up with trough. So a phase shift, a phase difference of 2 pi radians, these are actually called in phase. These are all called out of phase. So there's this idea of phase that you probably hear in your pre-calc classes. That's about differences in location or shifting of locations on waves relative to other waves, or places on waves relative to other places. Okay, so just look for these ideas of things being in phase or out of phase, and be able to identify how far out of phase things might be based on how far one wave is shifted over relative to another. Right? There's in phase because trough lines up with trough. Here's out of phase because peak lines up with trough. Here's back to in phase because trough lines up with trough. Okay? Okay, folks, I think that's all for today. We need to be able to identify what waves do when they encounter boundaries, and a boundary is a transition between one medium and another medium. It depends on the nature of the boundary itself. Okay, we need to be able to talk about what happens when waves that are approaching each other end up occupying the same place at the same time. They can interfere in one of a couple of waves, one of a couple of ways, constructively or destructively. Right, we can model those interferences in some specific cases. And then there's this idea of when will waves interfere constructively or destructively in terms of how in phase or out of phase are waves or places on waves. Okay? Okay.